Okay, so hi guys, my name is Jeff. I'll start us off. We got a bunch of people talking and not a lot of time. But the work I'm going to present today is on doing user-assisted reassembly of artifacts. And it can be, in this case, I focus on pottery that was unearthed at the National Constitution Center downtown. But our work also applies to things like paleontology or forensics, like broken anything. So just to motivate the problem a little bit, archaeologists, these are actual pictures from downtown. So they found all these privies. These are actually outhouses where people throw their broken or pots they're not into anymore. They just chuck them all in here. So these guys go through all the trouble of pulling them out of the ground and grouping them into sort of similar colors and textures. Like if you throw a pot in the ground, then most of the pieces are going to be pretty close to each other. So they try to catalog that, and then they just load up warehouses. So in this case, there's actually over 1 million different fragments that they pulled out of the ground. And then volunteers and archaeologists will then try to reassemble the broken objects. And that's where my work comes in. We're basically trying, this is supposed to be a red box right here, we're trying to basically make a digital version of the archaeologist reassembly table. Yeah, there we go. So the title is weird, right? The title of this work is Aligning Surfaces Without Aligning Surfaces. Just wanted to have a slide in here where I describe what that means. This is somebody else's work where they do volumetric reassembly. So in this case, you have full 3D models of each piece, and for pieces that match, like these two pieces will fit together, they have this rich surface that you can use to look for features, or you can use that rich 3D geometry to figure out which pieces fit together and also how they fit together. So in our case, we don't have that information. We just have a color image and a depth image. So we have 640 by 480, we have two images. We have one that's color information, and then the other image is just depth, how far away each point on the pottery fragment is. And we get this information using a 3D rangefinder. It basically beams a sheet of laser across the object and figures out its 3D geometry using that. So in this case, we have no break surfaces. Instead, we just have break contours. This edge here is going to line up with some other fragment's edge. And because we're looking only at the edges of each piece, our work is applicable not just to volumetric reassembly, but also can be used in forensics and paleontology, and stitching together any sort of two-dimensional surface in a 3D space. So the basic flow for our application is we first take all the raw data and represent it in these color images that I'll talk about shortly. We then use these images to find views or find fragments that align with each other and where they align. Then we stick them together. We make sure that the resulting new metafragment is nice and smooth, glue them together, and we just repeat this process over and over again until the object is complete. So the first thing I'll talk about is the boundary contour representation. Okay, so we represent the boundary of the piece using 4 different things. They break down into 2 categories. The geometry we represent using curvature and torsion. And the curvature is pretty intuitive. Right here it's going to be highly curved. Torsion is sort of the next step. It defines how much the curve is twisting. But basically these 2 values will uniquely describe the boundary contour, the triangle part, of each piece. I'm just going to show that again. And then also, as we move around the boundary, we're looking at the color. It's kind of hard to see, but we look at the red and green chromaticity, and these 2 values basically tell us what the color looks like at each point along the boundary. Okay, so we extract the raw values, put them at the base of the image, and then smooth the image as we go up. And what that does is it eliminates all the little subtle details and basically makes a very smooth version of each piece, so that we can deal with real-world issues like noise and just subtle detail. So the next thing is to find the fragments that match with each other. So like I just showed you, we make these images for 2 different fragments. So this top one is this bigger piece, and the triangle piece is this image here. And we basically use, the first step is we use longest common substring. It's probably an algorithm you guys have seen before. And we find the sequence of pixels on the top row that are the same, both images. Now, because we've blurred the actual real values a lot up to the top here, there's going to be some error. I mean, you can see just that the red and white lines aren't lining up with each other. So the next step is to refine that using cross-correlation. So we basically keep one box fixed, I believe it's this guy, and then we move this guy around until it aligns as well as it can with that there. So I'll just go back and forth one more time. So you can see the yellow box here moves to the right, and the triangle shifts up a little bit. So there's one more issue to deal with, and that's that these corner values are they don't match with each other, right? As soon as you move away from each other, they're going to have non-matching values. And because we've smoothed them, you can see that their effect fans out. So what we do then is we just expand the base of these regions until some amount of error has been surpassed. So now you can see that the red line is now the whole distance. I'll just go back a step, and then you can see these 2 regions are filled in. Okay, so that's the beginning of the algorithm. It basically finds matching fragments, sees how well they align, and then what we do is the alignment part. So the first thing is, now that we've found these 2 curves, these 2 subcontours of 2 different matching pieces, that basically tells us we can put these 2 pieces next to each other. But since we're only looking at the very extreme geometry, the boundary contour of each piece, we haven't done anything to align the actual surfaces of the pieces. So I usually talk about this as a hinge. You can see that the surfaces are not smooth. We look at that in terms of the surface normals. So the next thing is to place these 2 pieces next to each other and then find that angle, the hinge angle, that will make the 2 surfaces as smooth as possible. And once we do that, we can see that the surface normals will be nicely oriented, and we get a nice smooth match. So after we do that, we show the result to a user. The user gives us a thumbs up or thumbs down. If it looks right to the user, then we'll continue and move forward. Otherwise, we throw that away. And that process is just repeated until the vessel is complete. Now, there's actually one problem with this, and since I made these slides, I've expanded it a little bit. So I tacked on this extra block down here. And what we're doing is, when you have a group of pieces like this, we're only doing pairwise alignment, right? So in the end, you're accumulating all this error. So now, even though this little curve here should align with this curve here, the way I've presented it so far can't do anything about that. But we've extended it now so that we actually find these matching values, and we'll then adjust the alignments of all the other fragments to account for that new information. So the end result, I guess I'll show next there, yeah, is that this gap is closed. Oh, and then here's like a later on version from the bottom of that. You can see that all of these fragments, the ones that have the light purple, all of them have been realigned to account for the addition of this green edge here. So we made this big bowl, right? And it's like all the pieces are tacking onto each other, and at the end there's a huge gap. But now, with this new addition, we can find that these 2 pieces should align and tighten up the entire vessel to account for that. So this is an abridged example. I've eliminated like some of the computation time. I don't know what those white boxes are, but you can see that when the suggestion shows up in green, the purple ones indicate which other edges have been re-optimized to account for that new information. So in this case, there's nothing else to fix. You'll see that this error accumulates until the last step. So there, see, that's a pretty big gap. And in the next step, it just closed it, and all these purple ones have been re-optimized to account for that. just about out of time. We can look at some results.